Welcome to Openstax Contemporary Mathematics, Chapter 3, Section 4, Rational Numbers. Figure 320. Stock gains and losses are often represented as percentages. And shows on paper a bunch of charts with rising and falling and labels with dates and all that good stuff. Learning objectives. 1. After completing this section, you should be able to 1. Define and identify numbers that are rational. 2. Simplify rational numbers and express in lowest terms. 3. Add and subtract rational numbers. 4. Convert between improper fractions and mixed numbers. 5. Convert rational numbers between decimal and fraction form. 6. Multiply and divide rational numbers. 7. Apply the order of operations to rational numbers to simplify expressions. 8. Apply density property of rational numbers. 9. Solve problems involving rational numbers. 10. Use fractions to convert between units. 11. Define and apply percentage. 12. Solve problems using percent. We are often presented with percentages or fractions to explain how much of a population has a certain feature. For example, the 6-year graduation rate of college students at public institutions is 57.6%, or 72 out of 125. That fraction may be unsettling, but without the context, the percentage is hard to judge. So how does that compare to private institutions? There, the 6-year graduation rate is 65.4%, or 327 out of 500. Comparing the percentages is straightforward, but the fractions are harder to interpret due to denominators. For more context, historical data could be found. Pause. Continue. Defining and identifying numbers that are rational. A rational number, called rational since it is a ratio, is just a fraction where the numerator is an integer and the denominator is a non-zero integer. As simple as that is, they can be represented in many ways. It should be noted here that any integer is a rational number. An integer n written as a fraction of two integers is n divided by n divided by 1. In its most basic representation, a rational number is an integer divided by a non-zero integer, such as 3/12. Fraction may be used to represent parts of a whole. The denominator is the total number of parts to the object, and the numerator is how many of those parts are being used or selected. So if a pizza is cut into 8 equal pieces, each piece is 1/8 of the pizza. If you take 3 slices, you have 3/8 of the pizza. Similarly, if in a group of 20 people, 5 are wearing hats, then 5 out of 20 of the people are wearing hats, or 5/20ths. So figure 321, pizza cut in 8 slices with 3 slices highlighted. That's the 3/8. And then figure 322, group of 20 people with 5 people wearing hats. So it's just 20 figures of people and 5 of them have hats on. Another representation of rational numbers is as a mixed number, such as 2 and 5/8. This represents a whole number, 2 in this case, plus a fraction, the 5/8. Figure 323. 2 whole pizzas and 1 partial pizza. So it shows 8/8, 8/8, and 5/8. Rational numbers may also be expressed in decimal form, for instance, as 1.34. When 1.34 is written, the decimal part, 0.34, represents the fraction 34 hundredths. And the number 1.34 is equal to 1 and 34 hundredths. However, not all decimal representations are rational numbers. A number written in decimal form where there is a last decimal digit after a given decimal digit, all following decimal digits are 0, is a terminating decimal, as in 1.34 above. Alternately, any decimal numeral that, after a finite number of decimal digits, has digits equal to 0 for all digits following the last non-zero digit. All numbers that can be expressed as a terminating decimal are rational. This comes from what the decimal represents. The decimal part is the fraction of the decimal part divided by the appropriate power of 10. That power of 10 is the number of decimal digits present. as for 0.34, with 2 decimal digits being equal to 34 hundredths. Another form that is a rational number is a decimal that repeats a pattern, such as 67.1313 ... When a rational number is expressed in decimal form and the decimal is a repeated pattern, we use a special notation to designate the part that repeats. For example, if we have the repeating decimal 4.3636 ... we write this as 4.36 with a bar over the 36. The bar over 36 indicates that the 36 repeats forever. If the decimal representation of a number does not terminate or form a repeating decimal, that number is not a rational number. One class of numbers that is not rational is the square roots of integers or rational numbers that are not perfect, squares, such as square root 10 and square root 25/6. More generally, the number b is the square root of the number a if a equals b squared. The notation for this is b equals square root a, where the symbol, it's almost like a check mark, is the square root sign. An integer perfect square is any integer that can be written as the square of another integer. A rational perfect square is any rational number that can be written as a fraction of 2 integers that are perfect squares. Sometimes you may be able to identify a perfect square from memory. Another process that may be used is to factor the number into the product of an integer with itself, or a calculator, such as Desmos, may be used to find the square root of the number. If the calculator yields an integer, the original number was a perfect square. Tech check. Using Desmos to find the square root of a number. When Desmos is used, there is a tab at the bottom of the screen that opens the keyboard for Desmos. The keyboard is shown below. On the keyboard, figure 324, is the square root symbol. To find the square root of a number, click the square root key and then type the number. Desmos will automatically display the value of the square root as you enter the number. Figure 324, Desmos keyboard with square root key. So we have, it looks like 4 rows. Row 1, x, y, a squared, b squared. There's a space between that and the next. 7, 8, 9 divided by sign, space, functions. Second row, left parentheses, right parentheses, left bracket, right bracket. Oh, sorry. Less than, greater than, space, 4, 5, 6 times, space, left arrow, right arrow. Third row, absolute value A, so that's just some variable A, and then comma, less than or equal to, greater than or equal to, space, 1, 2, 3 minus, space, backspace. And then the last row, ABC, guessing that's an alphabet. There's a sound key, or it's like a volume button. Maybe it changes sounds or something. Square root key, pi key, space, 0, decimal, equal, plus, space, enter. Example 351. Identifying perfect squares. Which of the following are perfect squares? 1, 45. 2, 144. Solution. 1. We could attempt to find the perfect square by factoring. Writing all the factor pairs of 45 results in 1 times 45, 3 times 15, and 5 times 9. None of the pairs is a square, so 45 is not a perfect square. Using a calculator to find the square root of 45, we obtain 6.708, rounded to 3 decimal places. Since this was not an integer, the original number was not a perfect square. 2. We could attempt to find the perfect square by factoring. Writing all the factor pairs of 144 results in 1 times 144, 2 times 72, 3 times 48, 6 times 24, 8 times 18, and 12 times 12. Since the last pair is an integer multiplied by itself, 144 is a perfect square. Alternately, using Desmos to find the square root of 144, we obtain 12. Since the square root of 144 is an integer, 144 is a perfect square. Your turn 351. Determine if the following are perfect squares. 1, 94, 2, 441. Video, Introduction to Fractions. Example 352. Identifying rational numbers. Determine which of the following are rational numbers. 1, root 73, 2, 4.556, 3, 3 1/5, 4, 41 17ths, 5, 5.6 far with the bar, 5.64 with the bar over it. 5.64 with the bar over the 6.4. Solution. 1. Since 73 is not a perfect square, its square root is not a rational number. This can also be seen when a calculator is used. Entering square root 73 into a calculator results in 8.54400374531.7, and then more decimal values after that. There is no repeated pattern, so this is not a rational number. 2. Since 4.556 is a decimal that terminates, this is a rational number. 3. 3 1/5 is a mixed number, so it is a rational number. 4. 41/17 is an integer divided by an integer, so it is a rational number. 5. 5.646464 ... is a decimal that repeats a pattern, so it is a rational number. Your turn 352. Determine which of the following are rational numbers. 1. Square root 13. 2. Negative 13.21, the bar over the 2, 3. Negative 48 over negative 16. 4. Negative 4 and 18/19. 5. 14.1131. Simplifying rational numbers and expressing in lowest terms. A rational number is one way to express the division of two integers. As such, there may be multiple ways to express the same value with different rational numbers. For instance, 4/5 and 12/15 are the same value. If we enter them into a calculator, they both equal 0.8. Another way to understand this is to consider what it looks like in a figure when two fractions are equal. In figure 3.25, we see that 3/5 of the rectangle and 9/15 of the rectangle are equal areas. So we have figure 3.25, two rectangles with equal areas. So we have a 3x5 rectangle and a 3x5 rectangle, with the one on the left having each row between boxes highlighted. So the first three goes. So I'll say the rows. So row 1, 1, 2, 3. Row 2, 1, 2, 3. Row 1 has 3 boxes. Row 2 has 3 boxes. Row 3 has 3 boxes. Row 4, row 5 all have 3 boxes. But the columns are not divided. So it's just 5 little rectangles broken up with 3 of them shaded in. And then in the right rectangle, same thing as the left, but all 3 of the rows are divided, all 3 of the columns are divided by 2 lines. And so there are 15 little boxes and 9 of them are highlighted, but it's the same size. Sorry, I didn't mean to overcomplicate that. They are the same proportion of the area of the rectangle. The left rectangle has 5 pieces, 3 of which are shaded. The right rectangle has 15 pieces, 9 of which are shaded. Each of the pieces of the left rectangle was divided equally into 3 pieces. This was a multiplication. The numerator describing the left rectangle was 3, but it becomes 3 times 3, or 9, as each piece was divided into 3. Similarly, the denominator describing the left rectangle was 5, but became 5 times 3, or 15, as each piece was divided into 3. The fractions 3/5 and 9/15 are equivalent because they represent the same portion, often loosely referred to as equal. Excuse me. This understanding of equivalent fractions is very useful for conceptualization, but it isn't practical in general for determining when 2 fractions are equivalent. Generally, to determine if the 2 fractions a over b and c over d are equivalent, we check to see that a times d equals b times c. If those 2 products are equal, then the fractions are equal also. Example 353. Determining if 2 fractions are equivalent. Determine if 12/30ths and 14/35ths are equivalent fractions. Solution. Applying the definition, a equals 12, b equals 30, c equals 14, and d equals 35. So a times d equals 12 times 35 equals 420. Get lit. Also, b times c equals 30 times 14 equals 420. Double lit. Since these values are equal, the fractions are equivalent. Your turn 353. Determine if 8/14 and 12/26 are equivalent fractions. That A times D equals B times C indicates the fractions A over B and C over D are equivalent is due to some algebra. One property of natural numbers, integers, and rational numbers, also irrational numbers, is that for any three numbers A, B, and C, with C does not equal 0, if A equals B and A divided by C equals B over C, in other words, when two numbers are equal, then dividing both numbers by the same non-zero number, the two newly obtained numbers are also equal. We can apply that to A times D and B times C to show that A divided by B and C divided by D are equivalent if A times D equals B times C. If A times D equals B times C and C does not equal 0 and D does not equal 0, we can divide both sides by and obtain the following. We have A times D all over C equals B times C all over C. We can divide out the C on the right-hand side of the equation, resulting in A times D divided by C equals B. Similarly, we can divide both sides of the equation by D and obtain the following. A times D divided by C times D equals B divided by D. We can divide out D on the left-hand side of the equation, resulting in A divided by C equals B divided by D. So the rational numbers A over C and B over D are equivalent when A times D equals B times C. Video, equivalent fractions. Excuse me. Recall that a common divisor or common factor of a set of integers is one that divides all the numbers of the set of numbers being considered. In a fraction, when the numerator and denominator have a common divisor, the common divisor can be divided out. This is often called canceling the common factors, or more colloquially, as canceling. To show this, consider the fraction 36 divided by 63. The numerator and denominator have the common factor 3. We can rewrite the fraction as 36/63 equals 12 times 3, all divided by 21 times 3. The common divisor 3 is then divided out or canceled, and we can write the fraction as 21 times 3, where the 3 is crossed out, divided by 21 times 3, with the 3 crossed out, equals 12 over 21. The 3's have been crossed out to indicate they have been divided out. The process of dividing out two factors is also referred to as reducing the fraction. If the numerator and denominator have no common positive divisors other than 1, then the rational number is in lowest terms. The process of dividing out common divisors of the numerator and denominator of a fraction is called reducing the fraction. One way to reduce a fraction to lowest terms is to determine the GCD of the numerator and denominator and divide out the GCD. Another way is to divide out common divisors until the numerator and denominator have no more common factors. So, example 354. Reducing fractions to lowest terms. Express the following rational numbers in lowest terms. 1. 36/48. 2. 100/250. 3. 51/136. Solution. One process to reduce 36/48 to lowest terms is to identify the GCD of 36 and 48 and divide out the GCD. The GCD of 36 and 48 is 12. Step 1. We can then rewrite the numerator and denominator by factoring 12 from both. So 36/48 equals 12 times 3, all divided by 12 times 4. Step 2. We can now divide out the 12s from the numerator and denominator. So 36/48 equals 12 times 3, all divided by 12 times 4, but the 12s cancel. And that all equals 3/4. So when 36/48 is reduced to lowest terms, the result is 3/4. Alternately, you could identify a common factor, divide out that common factor, and repeat the process until the remaining fraction is in lowest terms. Step 1. You may notice that 4 is a common factor of 36 and 48. Step 2. Divide out the 4, as in 36/48 equals 4 times 9 divided by 4 times 12 equals 4 times 9 divided by 4 times 12, the 4 is crossed, equals 9/12. Step 3. Examining the 9 and 12, you identify 3 as a common factor and divide out the 3, as in 9/12, which equals 3 times 3 divided by 3 times 4, 3's cancel, and that equals 3/4. The 3 and 4 have no common positive factors other than 1, so it is in lowest terms. So when 36/48 is reduced to lowest terms, the result is 3/4. 2. Step 1. To reduce 100 2/50ths to lowest terms, identify the GCD of 100 and 250. This GCD is 50. Step 2. We can then rewrite the numerator and denominator by factoring 50 from both. So we get 100 to 2/50ths equals 50 times 2 divided by 50 times 5. Step 3. We can now divide out the 50s from the numerator and denominator. 100 2/50ths equals 50 times 2 divided by 50 times 5. The 50s cancel, get 2/5. So when 100 2/50ths is reduced to lowest terms, the result is 2/5. 3. Step 1. To reduce 51 136 to lowest terms, identify the GCD of 51 and 136. This GCD is 17. Step 2. We can then rewrite this numerator and denominator by factoring 17 from both. So 51 136 equals 17 times 3 divided by 17 times 8. Step 3. We can now divide out the 17s from the numerator and denominator. 51 136 equals 17 times 3 divided by 17 times 8. Cancel the 17s, equals 3/8. So when 51 136 is reduced to lowest terms, the result is 3/8. Your turn 354. Express 252 8/40ths in lowest terms. Video. Reducing fractions to lowest terms. Tech check. Using Desmos to find lowest terms. Desmos is a free online calculator. Desmos supports reducing fractions to lowest terms. When a fraction is entered, Desmos immediately calculates the decimal representation of the fraction. However, to the left of the fraction, there is a button that, when clicked, shows the fraction in reduced form. Video. Using Desmos to reduce a fraction. Adding and subtracting rational numbers. Adding or subtracting rational numbers can be done with the calculator, which often returns a decimal representation, or by finding a common denominator for the rational numbers being added or subtracted. Tech check. Using Desmos to add rational numbers in fractional form. To create a fraction in Desmos, enter the numerator, and then use the division key in the keyboard, and then enter the denominator. The fraction is then entered. Then, click the right arrow key to exit the denominator of the fraction. Next, enter the arithmetic operation, plus or minus, then enter the next fraction. The answer is displayed dynamically, calculates as you enter. To change the Desmos result from decimal to form to fractional form, use the fraction button, figure 326, on the left of the line that contains the calculation. And then figure 326. So the fraction button is a box with a line under it, and then a box. Kind of like, looks like the reverse of Pong. So Pong, you have two lines and then a little dot that goes back and forth. This is a line with two little dots like that. Example 355. Adding rational numbers using Desmos. Calculate 23 40seconds plus 9/56 using Desmos. Solution. Enter 23 40seconds plus 9/56 in Desmos. The result is displayed as 0.708333333, which is 0.7083 with a bar over the 3. Clicking the fraction button to the left on the calculation line yields 17/24. Your turn 355. Calculate 124 over 297 plus 3 over 125. Performing addition and subtraction without a calculator may be more involved. When the two rational numbers have a common denominator, then adding or subtracting the two numbers is straightforward. Add or subtract the numerators, and then place that value in the numerator and the common denominator in the denominator. Symbolically, we write this as A over C plus or minus B over C equals A plus or minus B all over C. This can be seen in figure 327, which shows 3/20ths plus 4/20ths equals 7/20ths. So here we go. Figure 327, partially shaded rectangle. We have a 4x5, no, it's 1, 2, 3. Yeah, 4x5 rectangle. That's 20 pieces. They shaded the first 4 and the bottom 3. And shows that total is 7. It is customary to then write the following in lowest terms. Formula. If C is a non-zero integer, then A divided by B plus or minus B divided by C equals numerator a plus or minus b, denominator c. Example 356. Adding rational numbers with the same denominator. Calculate 13/28 plus 7/28. Solution. Since the rational numbers have the same denominator, we perform the addition of the numerators, 13 plus 7, and then place the result in the numerator and the common denominator, 28, in the denominator. So 13 over 28 plus 7 over 28 equals 13 plus 7, all over 28 equals 20 over 28. Once we have that result, reduce to lowest terms, which gives 20/28 equals 4 times 5 divided by 4 times 7 equals, so that the 4's cancel, you get 5/7. Your turn, 356. Calculate 38/73 plus 7/73. Example 357. Subtracting rational numbers with the same denominator. Calculate 45 over 136 minus 17 over 136. Since the rational numbers have the same denominator, we perform the subtraction of the numbers 45 minus 17 and then place the result in the numerator and the common denominator, 136, in the denominator. So we have 45, 136 minus 17, 136. They both go in the numerator, so you get 45 minus 17 all over 136. That equals 28 over 136. Once we have that result, reduce to lowest terms. This gives 28 136 equals 4 times 7 over 4 times 34. 4's cancel, 7/34. Your turn, 357. Calculate 21 over 40 minus 8 over 40. When the rational numbers do not have common denominators, then we have to transform the rational numbers so that they do have common denominators. The common denominator that reduces work later in the problem is the LCM of the numerator and denominator. When adding or subtracting the rational numbers a over b and c over d, we perform the following steps. Step 1. Find LCM of BD. Step 2. Calculate n equals numerator LCM BD all over b, and m equals numerator LCM of BD all over d. Step 3. Multiply the numerator and denominator of a over b by n, yielding a times n divided by b times n. Step 4. Multiply the numerator and denominator of c divided by d by m, yielding c times m divided by d times m. Step 5. Add or subtract the rational numbers from step 3 and 4, since they now have the common denominators. You should be aware that the common denominator is LCM BD. For the first denominator, we have b times n equals b times numerator LCM BD all over b, which equals LCM BD. Since we multiply and divide LCM BD by the same number for the same reason, d times m equals d times numerator LCM BD all divided by b equals LCM BD. Example 358. Adding rational numbers with unequal denominators. Calculate 11/18 plus 2/15. Solution. The denominators of the fractions are 18 and 15, so we label b equals 18 and d equals 15. Step 1. Find LCM 18, 15. This is 90. Step 2. Calculate n and m. n equals 90 over 18 equals 5, and m equals 90 over 15 equals 6. Step 3. Multiplying the numerator and denominator of 11/18 by n equals 5 yields 11 times 5 divided by 18 times 5, which equals 55/90. Step 4. Multiply the numerator and denominator of 2/15 by m equals 6 yields 2 times 6 divided by 15 times 6 equals 12/90. Step 5. Now we add the values from steps 3 and 4. 55/90 plus 12/90 equals 67/90. This is in lowest terms, so we have found that 11/18 plus 2/15 equals 67/90. Your turn, 358. Calculate 4/9 plus 7/12. All right, let's go ahead and stop there. It's about 30 minutes.